Hello students. So let us continue with the functions concept. In the last class we have come to know about the definition of the function and how to do the one-one and types of functions like one-one and onto functions, and how to apply the definition in problem also. Now let us continue with the problems once again. See. So with the same exercise 1.2. So one more problem I have written here. State whether the function is 1, 1, onto or bijective. The function is defined in the set R to R, defined as f of x is equal to 1 plus x square. The procedure will remain same as we have done in the last video. Okay. So same thing. First I have to prove 1, 1. Whether the given function is 1, 1 or not, whether I have to check that first. So 1, 1. For that, as usual, I will consider the two elements. Let x1 comma x2 belongs to R. That is, here we will consider the domain set such that f of x1 is equal to f of x2. You people know the procedure, right? So I will continue with the problem. So f of x1 is equal to f of x2. So 1 plus x1 square is equal to 1 plus x2 square. So 1 1 we can leave on both sides. So it will be x1 square is equal to x2 square. Is x1 is equal to x2 in real numbers? We have already learned about this square term, correct? Square term is always positive. So when the term is squared, they both will be equal. Is the terms are equal here in real numbers? No, they are not equal. In the last class we have learned because for, as we can consider the example, because minus 2 comma plus 2 we will consider belongs to R, but here see f of minus 2 will be equal to f of 2, correct? Because minus 2 whole square is also 4, plus 2 whole square is also 4. That means minus 2 whole square is also 4, plus 2 whole square is also 4. But is minus 2 is equal to plus 2? No, minus 2 cannot be equal to plus 2. But minus 2 whole square and plus 2 whole square will converge for only same element. They will be having, see, 1 plus x1 whole square, 1 plus x2 whole square will be having the same image in the codomain. But both the terms are equal? Is minus 2 is equal to the plus 2? No, they cannot be equal, correct? So I have written here f of minus 2 is equal to f of 2. That is 1 plus minus 2 whole square is equal to 1 plus 2 square. The functions will be equal, but the terms are not equal. That means minus 2 and plus 2 will be having same image, but the terms are different. So it violates the 1, 1 function, correct? It violates the rules of 1, 1 function. So the given function is not 1, 1. So I conclude it. So therefore, f is not 1, 1. When does not obeys, we should give example that it is given. Okay. Let us see whether the function is onto or not. Onto function. Onto. Same procedure. I will consider an element y in the codomain. Such that there exists in x belongs to R, that means in domain, that is y is equal to f of x, correct? There exists an element x in domain which will be, the function will be equal to the y. So what is y? Y is equal to, what is f? 1 plus x square, correct? Now we will extract the value of x. X square is equal to y minus 1, right? X is equal to plus or minus root of y minus 1. Does this belongs to the R? Does this belongs to the R? No, obviously it does not belongs to R. Why? Very simple, we can do it by example, correct? We can do it by example. I can consider minus 3 belongs to R, correct? Minus 3 belongs to R, but what? X is equal to root of minus 3 minus 1, which will get me the answer as root of minus 4, that is equal to I2. correct, which is a complex number which does not belongs to R. So what is the conclusion of this? F is not 1, 2, isn't it not? So what I can conclude, F is not onto. Is it 1, 1? Not onto. F is not 1, 1 also. It is not onto also. Then what I can conclude? Obviously F is not bijective function. So according to the question, is 1, 1 onto or bijective? Neither it satisfies, right? So what I can conclude here, so I get the conclusion here, F is not bijective function. Is not bijective function under the set R. Okay. Let us continue with one more problem. Now let us take one special function. Okay. Here show that f from R to R, that is the function is defined from real numbers to real numbers, given by f of x is equal to the greatest integer function, as you know, correct? It's a greatest integer function where its value will remain less than or equal to x itself, right? The greatest integer function value will remain less than or equal to x itself. I have to show this greatest function as neither 1, 1 nor 2. You have studied about this greatest integer function in the first PUC syllabus, right? So let us see whether it satisfies or not. Neither 1, 1 nor 2 I have to show. So as usual, I will start with the procedure. That is for 1, 1 first. As usual procedure, let x1 comma x2 belongs to the real numbers, that is codomain. You already know, sorry, domain. People already know, such that f of x1 is equal to f of x2. That is greatest integer x1 is equal to greatest integer x2. If greatest integer x1 is equal to greatest integer x2, is x1 is equal to x2? We know that they both cannot be equal. Correct? They both cannot be equal. Why they cannot be equal? Let us learn it by example. Okay? Example. So you know the concept of greatest integer, right? So let us see what is the greatest integer value of 1.3. The greatest integer value of 1.3. As you know its answer, its value will always remain less than or equal to the integer itself. What is the integer here? 1. So the greatest integer value of 1.3 is 1. And what is the greatest integer value of 1.9? The greatest integer of value of 1.9 is also 1. Correct? That means they both will merge for one image. The greatest integer value of 1.3 is also 1. 1.9 is also 1. That means they both have only one image. So they are not 1, 1. Understand? So they are not 1, 1. Okay? So therefore, here what? They both have only one image, but 1.3 is not equal to 1.9. Correct? 1.3 is not equal to 1.9. So therefore, f is not 1, 1. Okay? So I like to explain once again. Let us consider the example. The greatest integer value of 1.3 is 1. The greatest integer value of 1.9 is also 1. So what it shows? The terms 1.3 and 1.9 have only one image, but elements are not equal to each other. So it's a many to one function. It is not 1, 1 function. Okay? So let us go to the next step. That is onto. Is it onto? Okay? See. Let. See, real numbers means it contains all kind of numbers, isn't it now? So you will consider here is the 5 by 2 belongs to R. Correct? 5 by 2 belongs to R. But I cannot find any greatest integer value which give me the answer as 5 by 2. Isn't it not? That means let 5 by 2 belongs to R, but there does not exist any f of x whose fraction. Has the greatest integer. It says greatest integer. It's an integer value. It will never give me a fraction. So f of x will never yield there, but there does not exist f of x is equal to 5 by 2. Correct? There does not exist any function which get me function the greatest integer function which get me the answer of fraction. So what is not? Because it is not onto. Okay, let us write the reason. What is the reason? Because f of x is a greatest integer function and it is an integer. It is an integer. It cannot be a fraction. So what I can conclude from this? F is not onto. F is not an onto function. So the greatest integer function is neither 1 nor onto. So what I can exactly conclude from this? I can conclude that f is not a bijective function. Bijective function. F is not an bijective function. As you know, this greatest integer function will come under special functions. It is one of the important results. Okay. Similarly, see, as you understood this, so let us learn about the one more special function, that is the modulus function. Okay, children. So here, show that f from R to R, the function only I will change it to modulus function. Modulus of x. As you know, its property. Modulus of x means its property is to convert the negative term into positive term. Isn't it not? The function of the modulus term is to convert the negative term into positive term. Isn't it not? So let us see whether it obeys the conditions or whether it does not obey the condition. Okay, let us see. Same procedure will start, that is 1 1. Okay, same I will consider the two elements in domain x1 comma x2 belongs to R in domain. Okay, such that f of x1 is equal to f of x2. F of x1 is equal to f of x2, that is modulus of x1 is equal to modulus of x2. Modulus of x1 is equal to modulus of x2. Is x1 is equal to x2? No, they both are not equal. Why? It's very simple. Maybe you people have already understood. Because the modulus of minus 2 is also plus 2 and plus 2 is also plus 2. That means they both have same image in the real numbers. Correct? That means they both have same image. That means two elements are having same image means it's many to 1. It cannot be 1 1. Isn't it not? So what I can conclude? Minus 1 comma minus 2 belongs to R. Right? Yeah, this implies that is f of minus 2 is equal to f of 2. Correct? F of minus 2 is equal to f of 2. But minus 2 will never be equal to 2. Minus 2 will never be equal to 2. So, because they both will be having same images. So, it is f is not 1 1. F is not 1 1. Okay. Let us move on to the another one, that is onto. The same like how we have proved for the greatest integer function. Because the set is given real numbers. In real numbers I can consider the negatives, positives, rationals, irrationals, anything. But do they element in the modulus function? They have the image that we have to check. Correct? So let us take an example. Same here. I will consider minus 3 belongs to R. Correct? Minus 3 is a real number which belongs to the R, that is it is a codomain set. But there exists no function. Correct? But there does not exist any function because f of x is a modulus function. The modulus function will always yield me the positive answer, that is greater 0 values, positive answers. But here the answer I am getting as negative term. So obviously that negative term will not come under the modulus function. So it does not have any pre-images in the domain. Understand? So it does not have any pre-images in the domain. So but there does not exist f of x is equal to minus 3 because, let me write the because reason, because f of x is equal to modulus of x is greater than 0 function. Correct? It's a positive value. Because. So therefore f is not onto. So as usual for the last, f is neither 1 nor onto. So this implies that f is not a bijective function. That's it. So that is about the results of the some special functions. So let us move on towards the one more, that is composition function. Okay. In composition function, we will be having 3 sets. So I will consider the 3 sets A, B and C. The set A and B is functioned by, let us function it by f, connected, mapped with the function f. The sets B and C are mapped with the function G. Okay. So what is the composition? If the set A is having the element x, this x is mapped with set B by using the function A. So in set B, its image will be like f of x. Correct? The element x, its image, how it will be image in set B? It will be like f of x, isn't it not? Then the set B is mapped with the set C by the function G. Now the element of set B is f of x. Correct? This f of x, how it will be defined in set C? Very simple, by using again the g function. So it will become here g of f of x. Okay. So this the connection of A to B and B to C, where the two or more functions are merged each other. Such functions are called as our composition functions. Clear? Such functions are called as our composition function. How it will be defined? The composition of f and g is defined as, it's very simple, g composition f of x. Correct? G composition f of x, because f is mapped with b and b is mapped with c. So it is A to C. Correct? So it is mapped as G composition f of x. This composition, this is the composition operator which will be written as small o. Okay? This is the composition operator. So how it will be functioning? It's very simple. It's g of, it is expanded as g of f of x. Clear? So here the f is, x is defined by the function f and f of x is defined by the function g. Here two functions are merged each other. Such functions are called as your composition functions. Okay. So how to do the problems on this basis? Very simple concept. Okay. See, let me consider example. Let us consider the sets. That is, I will take the set A. Okay. I will take the set A as 1, 2, 3. Set B has, okay, it is 5, 6, 7, and set C has 4, 8, 9. Okay. As we know, the set A to B is defined by the function f. So I map the terms. Very simple. Here the A to B, the function f is defined by A to B. The function f is defined by, the function, let us define the function A to B. Okay, how I can map it? Then it will become f of 1 is equal to 5, f of 2 is equal to 6, f of 3 is equal to 7. So I have considered the function from A to B. Now I am defining the function g. Now I have defined the function g from B to C. Okay. So let us map the sets B to C. So it is g of 5 is equal to 4, g of 6 is equal to 8, g of 7 is equal to 9. I have defined the function. See, one thing we have to observe here, the codomain of the function f will be the domain of function g. You have to observe that the codomain of the function f will be the domain of function g. So that will relate from f to g. Okay. Now, how to define this? An easy concept. So now let us take the composition of these two functions. Okay. See, this is the set defined from the function A to B containing the elements that is from B to C. Now let us take these functions composition. Now let us define the composition of terms, that is f composition from A to C, in which A will become the domain and set C will become the codomain. Now let us see how to get the values by using the composition by 3 sets. Okay. Now, so it will be from A to C. Then C, this can be defined as G composition f of 1. Correct? From set A, I have to take the domain. G composition f of 1. This can be written as G of f of 1. Isn't it not? This can be written as G of f of 1. What is f of 1? We have the f of 1 value. Correct? It is defined in the function f. So f of 1 is 5. So it will become G of 5. Now what is G of 5? It is also already been defined. So G of 5 is 4. So its value is 4. So what is the value of G composition f of 1? It is 4. See, now you have to observe that 1 belongs to the set A and 4 belongs to the set C. Correct? 1 belongs to the domain and 4 belongs to the set C, as you can see. So either we can map from A to C, as B will behave as, in the function f it will have codomain, in the function g it will behave as domain. Clear? Similarly, I can get related with the second element, that is G composition f of 2. This will get the value of G of f of 2. That is equal to G of, what is f of 2? F of 2 is 6. So G of 6 value will become 8. So G composition f of 2 value will be 8. Next, similarly, G composition f of 3. G composition f of 3 is equal to G of f of 3 is equal to G of, what is f of 3? F of 3 value is 7. So this is equal to G of 7 value is 9. So G composition f of 3 value will become 9. So like this we will define the composition function from A to C. Okay, where we will merge the two functions. Okay, it's a general set defining method. Clear? Let us see the one more function in composition functions. See, this kind of problems will be asked for 2 marks in the exams. Okay, so here I have to find G composition f and f composition g. And f is defined function from R to R, and g is also defined the function from R to R. F of x is given by the value, the function is given by the value cos x, and g of x, the function is given by 3x square. Let us see whether they both are equal or not. Okay, in solution. Very simple. First, G composition f of x. I have to find. This will be split as G of f of x. This can be split as G of f of x, where G of, let me define the f of x first. What is f of x? According to the question, f of x is cos x. Correct? F of x is g of x is defined as 3x square. So see the function and this term. In the place of x, the cos x we have. So in the term also, in the place of x, we will write the cos x. That's it. So this will be like 3 cos x square. X is squared, so cos x will also be squared. So this is our g conversion of x function. Now let us see the second one, that is f conversion g of x. This is written as f of g of x, that is equal to f of, what is g of x? Now we will define g of x first. So it is 3x square. Correct? G of x. Now it is visible like f of x, isn't it not? So f of x defined as cos x. So this can be written as cos of 3x square. Correct? Because in the place of x I have 3x square. So in function also in the place of x we will write 3x square. Okay? So this is our g conversion f and f conversion g functions. Are they equal? They will never be equal to each other. Because if I consider the function, it is defined from f to g. Correct? Here it is defined from g to f. So according to that basis, the domain of this will be over domain of this function, isn't it? So the function will be reversed, isn't it? So g conversion f is not equal to f conversion g. Is the conclusion for this problem. Clear? Let us see the one more function. The one more problem where f of x is defined as 8x cube and g of x is defined as x to the power of 1 by 3. We have to verify the same composition functions. Okay? So in solution, first I will verify for g composition f of x. So that is equal to the same method. First I will split it as g of f of x. Now let us write the value of f of x. The function of value of f of x is 8x cube. Correct? The function f of x value is 8x cube. Now it is like g of x now. So it will become, in the place of x I have 8x cube. So in term also in the place of x we will write 8x cube. So 8x cube to the power of 1 by 3. 8x cube to the power of 1 by 3. You know what is 1 by 3? 1 by 3 is nothing but the cube root. So its value will become 2x. Correct? Its value will become 2x. Now let us verify the second term, that is f conversion g of x. F conversion g of x is equal to f of g of x. We can split it like this. So that is equal to f of, now we have to write the g of x function inside. The g of x is x to the power of 1 by 3. X to the power of 1 by 3. Now that has to be applied to the function f. So then that will be changed as 8. In the place of x I have to write this term. So it is x to the power of 1 by 3 whole cube. X to the power of 1 by 3 whole cube. As you know, this 3 will get cancels. So we will get the answer as 8x. Are they equal? They are never equal. So what I can conclude from this, g conversion f of x is not equal to f conversion g of x. Is the problem. Let us see the one more problem. Here it is given that if f from a to b and g from b to c are 1, 1 and 1, both the functions are obeys the rule of 1, 1 also and 1, 2 also. That means the function f is bijective and the function g is also bijective. Then if they both individually bijective, I have to show their composition is also bijective. Clear? If the functions are individually bijective, that means 1, 1 and 1, 2 means I have to show their composition, that is f composition g is also bijective function. Let us see how to prove it. Okay, so as usual you know the process of 1, 1 and 1, correct? I will take same thing 1, 1 for the 1, 1 function. Okay, here as usual I will So let x1 comma x2 belongs to, because I am doing for the composition function, the composition function is defined from A to C, so I will consider the two elements in the domain of the composition function, that is A. Okay, x1 comma x2 belongs to A such that it is g composition f of x1 is equal to g composition f of x2. Correct? That will be split as g of f of x1 is equal to g of f of x2. Okay, now we know that g in the both sides, if they are common terms, if they have the same properties, I can leave those terms. According to that, see here the g is 1 1, so I can leave it. We know it is given, correct? It is given g from B to C is 1 1, so I can leave that term. Because why? Because g is 1 1. It is given in question only. It is given in question only. So g is 1 1, so I can leave those terms. I can get that f of x1 is equal to f of x2. Since according to the question, we know one more thing also, f is also 1 1. If f is also 1 1, what I can conclude? x1 is equal to x2. What gets me the proof? Why I can write like this? Because f is 1 1. Yeah? Because f is 1 1, so I can leave the function f on both sides and I can come to the conclusion that x1 is equal to x2. When the functions are equal, then their individual terms are also equals, means what it shows? Our composition, that is g composition f of x is an 1 1 function. Correct? Is an 1 1 function. Let us see whether it satisfies onto or not. Okay? So it's given that what it is given, f is also onto, g is also onto. I have to prove that. Yeah, g composition f is also onto. As usual, let us start with the same procedure. For that, initially what I will do, I will consider the terms in each set. Okay, I will consider that the terms in each set, that is let f of x is equal to x belongs to, correct? Okay. Let x belongs to A, y belongs to set B, and let x belongs to set A, y belongs to set B, and z belongs to set C. Okay, I will consider as each term in each set. Then, see, the composition function is defined from A to C, correct? Then how we can consider it? Then I can consider it as let y belongs to then we know that g of y is equal to z. Why g of y is equal to z? G of y is equal to z because g is onto and f of x is equal to y. Why f of x is equal to y? Because f is onto. Correct? F is onto. Then how to take g composition f? So it's very easy. So now consider g composition f of x. Correct? What it can be defined as g of f of x. Correct? So g of, what is f of x? F of x is y. What is g of y? G of y is z. Correct? F of x is y and g of y is z. So what I got the answer, g composition f of x is equal to z. That means it is because x belongs to A and z belongs to C. Then it proves the composition from, because the element x is connected from f of x to y, then g of y to z. Then I got the answer as g composition f of x as z. That means the composition from F to G is defined to A to C. So X belongs to the domain and Z belongs to the codomain. So it shows that our composition, G composition of X, is onto the given function F is 1 1. The composition function is 1 1 and also it is onto. So what it shows? The composition function is bijective. Okay, the composition function is bijective. So if individually the functions obeys the rules of 1 1 and onto, then its composition function will also be obeys the rules of 1 1 and onto. So this is about the composition function, students. So I hope you understood.